All right, so 11 o'clock. So welcome to this week's MateriAlZ seminar. Today we have a very special in-person seminar by Dr. Pascal Thome. Dr. Thome comes from the University of Bochum, Ruhr-University in Bochum. So in Germany, if you want to be an academic, you get your PhD degree, and then after your PhD degree, you have to get a habilitation degree. So that is what Dr. Thome is finishing up. He's finishing up basically his second PhD degree, which is the habilitation degree. So Dr. Thome is working on the cutting edge of materials science and materials informatics. He's actually doing a lot with microstructure, quantification, development of machine learning, AI technologies to make possible the collection of large data sets of microstructure that we can then translate into the development of digital twins, right, to enable industry 4.0 type technologies, right? So today's talk is going to be very exciting in terms of being able to fuse a couple of different technology areas, not just material science, but also in information communication technology. So with that, Dr. Thome.
Okay, thanks, Sammy, for this very kind and nice introduction. And it's my pleasure to present some of my results that I produced during my habilitation. And it will be about microstructure informatics, and we will talk about digital microscopy and quantitative characterization of microstructures. But there's actually much more to it, and you will see in a minute. So let me give you a quick overview about what I did in my career. So I started off as an experimentalist, which is kind of strange because most people who do informatics usually come from the simulation field. So I'm in my heart, I'm an experimentalist, right? So I started off with manufacturing. So I really stood in the labs and furnace producing material and characterized the processability. It didn't always work, as you can see here. So this material didn't want to get rolled, right? Yeah, and then later on, I did basic Martensite research. So by the way, the first materials was shared memory alloys. This shared memory effect is being realized by martensitic transformation. Later on, I did some basic research on martensitic transformation. It's kind of a very complex topic. There's a phenomenological theory of martensite transformations where you can calculate how a austenite lattice transforms into martensite variants by different shear operations and so on. And in this project, I already learned how to do advanced EBSD studies, because you can take an EBSD data set, you have all the orientations, and you can combine it with knowledge of martensitic transformations. So for example, what I was able to do is you measure a martensite microstructure there on the left, and you can recalculate how did the prior austenite grain structure look like. For example, if you want to investigate the distribution of grain sizes in austenite. Then later in my PhD, I stayed in the EBSD community and I developed my own indexation method, which has a much higher angular resolution than the conventional software that you can buy commercially. And I used it to characterize very fine misorientations in single crystal nickel-based superalloys. After my PhD, I started my habilitation. I became group leader in microstructure informatics. And the difference between a PhD and habilitation is in a PhD, you are very focused and narrowed down, usually to one specific research topic. And in the habilitation, you try to generalize certain ideas. You try to come up with something more significant. And of course, over the course of time, as you see, I became less and less of an experimentalist, and the models and mathematics became more complex up to today. But you can relax, so I will not talk about this at all today, because a part of the habilitation is also that the candidates get tested if they are able to perform in education. And as you know, in education, it's very important to be able to present a difficult topic as easy as possible. And this is my plan for today's talk. So I want to present the concepts and ideas that I developed in the easiest possible way. So what is microstructure informatics? Probably you have not heard about this. It's kind of a very new branch of science. And there are three important factors there. Microstructure. So actually this is in German, this is a beautiful definition. I think it kind of lost its beauty in the translation. But there's one important sentence here. The microstructure is characterized by the nature, shape, size, distribution, and orientation of the individual elements of the microstructure. So to make the microstructure visible, we have to use microscopy, ancient technique, very long history. And nowadays, these microscopes are digital, so they produce data. So we can use informatics to algorithmically process this data. And this is basically what I do. So let me give you a small motivations of what we, all of us, are probably trying to achieve. So you know that there are these relations between manufacturing, microstructure, and properties. And we want, basically this is all what we do in material science, we want to understand these things. And now the question is how to build up digital twins of these different things. And on the left and on the right, it is, I wouldn't say easy, but at least we kind of know what to do. For example, in the manufacturing, you yourself control the parameters, right? You control, for example, in a heat treatment, the temperature and the time. So you have two variables that you can store in a database. Same is true for the properties, right? We have very defined testing, like we can test, for example, hardness, and we get a value that we can store in a database. Of course, I know in detail it's very complicated now with the additive manufacturing and so on. But when it comes down to microstructure, things are getting a little bit weird, right? Because there's this huge variety of appearances. And the question is, well, what does it have a grain structure in common with the martensite, for example, or with the dendrite structure? So what kind of number should we assign to these microstructures to be able to build a digital twin? And of course, material scientists have done this for 100 years now. And what we usually do is stereology. So there's concepts like line intersection methods or STM grain size. So we can derive certain parameters, quantitative parameters. Nowadays, these parameters are oftentimes called descriptors, and there are always new descriptors coming up. So people try to describe the microstructure with parameter. And there are even approaches that use neural networks like encoder, decoder system. And you can transform such a microstructure image into something that is called a feature vector, for example, that can then be used in a model, or you can use it with a decoder to generate artificial new microstructures. However, this is very common in the simulation field, but I'm coming from the experimental field, and we need actually something a little bit else. So I came up with a completely different approach, and what I do is I want to build an exact twin, a lossless twin of all geometric information that is inherent to the microstructure. And I will show you how to do this. So this is a small outlook, what we will talk about. It's not chronologically, but the main topic is how to build up microstructure databases. This is the main result of my habilitation. And I came up with an approach that I call relational geometric ontology. It is based on geometric representations of microstructural entities. To be able to build up these microstructure databases efficiently, we might have to use computer vision approaches. Actually, this is not so important in my opinion, but I will still talk about this a little bit, and I will give you a few examples. Microstructure informatics can also be used to improve the performance of microscopes. For example, in orientation imaging, I've done a lot of work on this. Actually, I didn't want to cover this too much, but I was told that people might be interested in this, so I included it. I hope that the talk will not be too long for this. So before we start, let me remind you about what the raw data of microstructure actually is. So usually this, so the microscopes provide us with images, but an image in the computer world is nothing else than a table, right? It's a table of pixels, and when the number is small, the pixel is dark. If it's high, the pixel is bright. And I can use it to display it on the screen, but of course I can also numerically access it. For example, I could load up an image in Excel, and then I can make a histogram of grayscale values whatsoever. If we have multiple micrographs, which usually we have, we need to organize these micrographs in some way, or these images. And what we have to do there is we need to create an image database. So now I will take a completely different example from the internet, from the web page freepik.com, because they have images without copyright. So I hope I don't get into trouble when I show some of this. And another reason why I use this is we actually don't have such a nice image database in material science, right? Imagine how nice it would be, right, if you can type in, give me all images of a copper alloy, and then there are 100,000 micrograms of copper. But there are certain reasons why this doesn't exist. I know there are smaller databases in certain departments, but, well, we don't have something global or something like this. And this would probably be the next step, right, to somehow centralize these images and make them available, assign hashtags to them, to be able to search for certain types of micrographs. But this is not what I'm interested in. I'm not interested in the next step, but even more in the step behind the next step. And what do I mean by that? So let's extract one element of this image database, which is an image. Again, for the computer, this image is just a big column of numbers, right? The computer has no idea if this is a family playing there or if this is just a random noise. And what I try to do is, I want to build up basically a digital twin of the information that is stored in the image and build up databases of the encrypted image information. So what do I mean with encrypted? I don't mean like that it is a passcode secured or something encrypted. I mean that the information is somehow hidden, in the constellation of pixel values, right? In the arrangement of contrast and so on. And I want to extract this information. And one way of doing this is by using what I call relational geometric ontology. And ontology, by developing ontologies, we need to define, well, what are our entities, what are our relations, and so on. And entities is a word that comes from basic philosophy, basically from metaphysics, where people really think about, well, what is reality, what exists, what does not exist, and so on. So this image, for example, contains entities. Each entity belongs to an ontologic class, and each entity is characterized by class-specific attributes. For example, when I look at this image, I can directly identify 5 entities in the foreground. Let's forget about the background for now. 4 entities of the class person and 1 entity of the class ball. And I don't want to build up image databases. What I do build up databases where the entries of the databases correspond to the entities of the image. So let me give you a closer look about how these entries look like. So let's focus on entity 1. It belongs to the class person, and each entity needs to have certain attributes. Each entity must have an attribute, the location. And the location basically answers the question, on which image of which database does this entity exist? Right? It exists on this image, which is part of that database. Then it has geometric attributes. The geometric attributes tell you where on this image does this entity exist, and what shape does it have. And this is being stored with a geometric representation. In this case, this could be a polygon, right? This outer line that I've drawn around the person. Then there are a few class-specific attributes. For example, when we talk about person, this could be size, age, weight, gender, nationality, whatsoever. Some of these attributes can directly be derived from the image. So if I had a scale bar, I could measure the size of the person. Other attributes cannot be derived from the image. For example, the nationality, right? There's no way determining this. Maybe I could, if there's another database somewhere else, a registry of the government, I could, pull out some information and then assign the nationality if I wanted to, but not in the general case. And of course, these class-specific attributes only make sense for a person. If you think about the ball, it doesn't make sense to talk about nationality. But the ball could have an attribute, a diameter. Please keep the ball in mind. We will talk about this later once again. So then now we have talked about these what I call object entities, but now there's a crucial idea that I developed. The reality that surrounds us is not only made up from object entities, but there's also relations between these entities. And now we talk about a completely different type of entity, which is what I call a relation entity. For example, I can see that there are people throwing a ball in this image. So I can make up an entity which is for the class ball throw. And these relation entities, they look a little bit different than object entities. First, of course, also they need to have the information on which image of which database does this relation exist. But now it is not represented geometrically, but it links to already existing object entities. So I know that in this ball throw, entity 1, entity 3, and entity 5 are involved. And then there can be class-specific attributes, in this case, for example, the trajectory of the ball. And I could represent the trajectory of the ball with line segments. So now already the first interesting thing happens. If I have the trajectory of the ball, and if I assume a gravitational constant there, I could in theory calculate the velocity of the ball on top of its trajectory, right? And this would never be possible if I tried to come up with an equation based on the pixel level. How should I calculate the pixels to come up with the velocity of the ball? But if I extract these entities and assign meaningful attributes, this becomes certainly possible. So then there are probably even more relation entities, for example, neighborhoods, right? And the attribute of neighborhood could be the distance. And I already spent now quite a long time to hopefully not to bore you so much by using this very trivial example. But maybe this is also a good time to appreciate the human brain, right? If you look at this image, all of this becomes clear in a split of a second. But making the computer perform a similar task is actually quite challenging. And now imagine this is only done for one image, but this image database contains hundreds of thousands of images. So imagine I would do the same for hundreds of thousands of images. I could get access to completely different statistics. For example, I could pull out or filter out all entities of the class ball throw. And then I can find out, well, if there's a ball thrown, there's a very high probability that there are children around, maybe. And if I want to advertise my ball, if I'm a manufacturer, then I know I put my poster somewhere where there's children around and not somewhere else. Right? I mean, it's probably a silly example, right? I just want to make an example what kind of information we can do that. And if you understood this concept, this trivial concept, then you already have a good idea of what I'm doing. The only difference is, of course, I don't do it with random images from the internet. I do this with micrographs that we produce in our labs. And my entities don't belong to the class ball or person. My entities belong to classes like crystallite, pore, dendrite, dislocation, right? And these classes are very well-known microstructural entities that we have lots of information about. So let's see what happens. We can basically do exactly the same with grains. And please note that I can identify a grain, I can geometrically represent it. And it's important now that I just continue counting, right? I had 9 entities before, and now this is just the 10th entity. There's no problem that the grain can exist next to a ball or whatsoever, right? Because it's a general approach now. And one of the advantages of this approach, well, I believe one of the advantages is compared to like this descriptor models that many people from the simulation field use, is there's thousands of publications that investigate the influence of manufacturing process on the properties of grains, for example. We do not have thousands of papers that characterize the influence of manufacturing to some fancy type of feature vector, right? So this basically gives us 100% backwards compatibility to the 100 years of material science that we are doing. Well, then I can do the same, right? There are multiple grains here, and there's a neighborhood. The neighborhood in terms of grains is very interesting because it can be characterized as a grain boundary. Again, there's thousands and thousands of papers about the properties of a grain boundary. There are things like the misorientation. Is it the twin boundary, some special boundaries? You can calculate grain boundary energies whatsoever. And now I also know this image, for example, comes from a colleague of mine who actually did it the right way because he published a set of images together with his publication. So the location attributes here are easy, right? This entities exist on this image, which is part of this database, which even has a DOI. And I can continue here. For example, there's a very small little pore over there. And now I can start to use this database to do certain types of investigation. So you can see that this grain structure comes out from a heat treatment of 60 minutes. So now I could say, extract all grain entities after heat treatment of 60 minutes and extract all grain entities after heat treatment of 120 minutes, 200 minutes, whatsoever. And then I can compare the attributes of these grains and how the heat treatment influences these attributes. So I can do comparisons easily between entities that belong to the same class. But I can even do comparisons between entities of different classes as long as they share the same attributes. For example, the pore has as an attribute a diameter. And also the soccer ball that we saw before also has an attribute a diameter. So if I would do this for thousands of images from the internet and thousands of images of the micrographs, I could derive, well, the average soccer ball is much larger than the average pore in a microstructure. I know it sounds probably silly once again, but this is a true statement about our reality, and I can reflect this true statement in such an organized database. So
I can get rid of that.
Sorry?
Participant and enable closed caption.
Ah. So now let's have a closer look to these grains here. Actually, I did a small little project. I don't want to spend too much time on this, and I use the conventional computer vision approach to identify these objects. I mean, often it's not so easy. But what I can, for example, do is I can extract certain grains, and I can search for all relations of these grains, and I can identify the neighbors. Actually, this is, I thought it would be useless. I just want to put it as a teaser because later on we will see a better example for this. But when I was here, I realized, well, this might actually be of relevance. For example, if you are investigating abnormal grain growth, right, and you have the hypothesis that if you have abnormally large grains, probably the surrounding grains have certain types of attributes, properties. This is exactly the approach how you could do the statistics, right? You search for the largest grains in the database, extract them, search for its surroundings, and characterize them and compare them to ordinary grains or whatsoever. So when I've done this, I can basically transform such a what we call qualitative imaging method. It's just an SE image or a BSE image into something that is more, that behaves more like an EBSD type of data set, right? Because, for example, I can extract all the grain entities, and at the same time, I extract the attribute of the grain size, and I can either plot it visually or I can derive statistics, circularity, aspect ratio, whatever I want to do, right? You can derive dozens of different parameters there. And I actually, this is simple example one. I actually had a few more, but I decided, well, I will just screw them because the talk will be too long otherwise. So we directly jump into a little bit more real scientific project. And back in Bochum, we have a really, really large collaborative research center. There are different universities participating, for example, Erlangen and Bochum. There's the Max Planck Institute collaborating, also the German Center for Aerospace. And we are interested in nickel-based superalloys, especially single crystalline nickel-based superalloys. And one of the questions, or one of the research topics, is the solidification of single crystal superalloys, conventional but also additively manufactured. And the conventional process is basically a Bridgman furnace. You put the sample, you melt it, you cool down one side, and you slowly pull out the sample, and thus creating a temperature gradient, and all the crystal is forced to grow. It can only grow in one direction. We use a seeding technique. There's also a helix, a grain selector technique, but I don't want to talk about this much. And what's happening then is that the crystals that we are producing, they are not pure, right? There are crystal defects being introduced during the solidification. And one of these crystal defects is called crystal mosaicity. So in an ideal world, maybe I should mention that the solidification happens by the formation of dendrites, because there's chemical segregations happening, but this would be too much. And we are interested in the effect that these dendrites don't all grow parallel, but there are slight misorientations between these dendrites. And this is called crystal mosaicity. So we wanted to investigate this in 3 dimensions. We wanted to follow the growth path of each of these dendrites to see, well, what's happening there. Because there's this idea of competitive growth, right? These dendrites kind of fight a little bit against each other, and there are things like branching events and extinction events. And when we want to do this, we already have the first problem, because what we have is we have a serial sectioned sample. So we have hundreds of images that look like on the one shown on the right here. And the small little crosses are the dendrites. So the first problem we have is we need to identify the position of the dendrites. And for this, we tried it with conventional approaches from computer vision, like edge detection or whatever, but it turned out it didn't work because the morphology, there's too much fluctuation in the morphology. So we basically had to pull out the big guns, and the big guns in computer visions nowadays are deep learning neural networks. To develop such an architecture, it is a little bit tricky, right? It is different than conventional software processing, because these things, they can behave very strangely. You don't really know how they behave when you start off, so you kind of have to temper them. And also they have to be trained. So what you need is you need to have training data. In our case, this was a manually marked dendrite cores on an image. Then the detector is being trained, and by training, it tries to optimize the weights and the activation functions of its neurons. And once it's finished with training, you test it. And by testing, I mean, you put in some unknown data and you see how does the object detector perform. And then you will realize, oh, dang it, it doesn't work. Right? It's not able to detect the dendrites. So you need to identify why that is by comparing the detections with ground truth data. And because it doesn't work in the first sense, then what you have to do is you have to optimize, right? You have to reconfigure the network architecture, you have to change certain hyperparameters and so on. And probably the next iteration also doesn't work. So this is an iterative process which has to be repeated and repeated. Excuse me. However, if you do it in a smart way, you don't do it iteratively, but you do it in parallel, right? You directly do different architectures and different hyperparameters. And this is what we did. So we trained 11 different detector architectures with over 300 combinations of varying training parameters. And our network architecture actually consists of two networks. One is called a classification network. The other is called a sub-detection network. And then we just identify which of these combinations of training parameters and architectures works best. And in our case, the best performing network had about 99% detection rate with less than 1% of false positives. So now we are able to detect the locations of the dendrite cores on each individual slice, but we wanted to do this three-dimensional. So we had to stack up these images again and trace the growth path of each individual dendrite. We used an iterative closest points algorithm for this. And we had to consider that there are certain morphological relations, things like extinctions and branchings. This information is intermediately stored in so-called incident matrices, but they are not very practical to extract information. So what we did is what we always do, we transformed it into a relational geometric ontology. Now our entities are of the type dendrite. They are represented as line segments in 3D space, and the relations could be something like branching or extinction. Now what does come out of this? This is basically the data set that we have. You see it on the right. Each line segment there represents a dendrite in a volume of over 6,000 cubic millimeters. You can see some of these parameters here, right? We have detected 11,000 individual dendrites with over 180 individual detections. And there are actually about 30,000 relation entities. So there's much more relation entities than object entities, which is interesting. I believe that this is always the case. I'm not certain about this. And now the big question, of course, that you might ask, well, why did we do this? I mean, it looks nice, right? But we want to make use of it. So what can we do with such a database? Basically, everything that was possible before with manual microstructure characterization. So before I joined this project, my colleagues did it the old-fashioned way, and they marked all the dendrites, they printed it out on a huge piece of paper and traced where did they grow, and they characterized the orientation spread at 4 different points in the sample, bottom, middle, and top. Actually, to generate one of these data sets took about 3 weeks, right? For a full PhD, full time, 3 weeks. And what we can do now is basically the same, but completely automized, right? So we have this not on 4 places. We have characterized the orientation spread over the whole volume. And we are now slicing the sample from bottom to top. And you can see on the full figure, all the dendrites are slightly misorientated to the bottom right. This is why the whole field of dendrites moves to the bottom right also. And we have a continuous characterization of the whole volume. And now we can also see, well, how does the orientation spread depend on the growth distance of the dendrites? And we can see, which is interesting, there's actually a linear function between height of growth and deviation orientation spread. So what this means is the quality of the single crystal gets worse and worse and worse. So if you would try to produce a 1 meter long single crystal with Bridgman, you start off with a pretty good single crystal, then the crystal mosaicity gets worse, and on top you end up with a polycrystal. And you get to see this in this tendency here. But that's not all, right? So because I can do other things now, because we have not only identified the dendrites themselves, but we have also identified all their relations. So what we can do now is we can start with the dendrite and then iterate through all of its branching processes. In this way, we can reconstruct what we call dendrite families. So again, each line here is a dendrite, each color line, and it branches off, branches off, branches off. And now we get access to the nature of these dendrite families. And there are many interesting observations. Actually, nobody expected the dendrites to behave like this. You can see different types of bending. They're doing strange things. And to be frank, we now have more microstructure data than we can handle, right? We don't even know what to do with all this data. But I can show you why this is still a good approach. Yeah, this is just how I can access the data, right? I can access one object entity, find all its relations, then I get a set of branchings. Then I get a new set of dendrites, and I can iteratively search for all new branching and so on and so forth. So what I can then do is I can search the database for special dendrite constellations. For example, we were interested in the interaction between the dendritic growth and the sample, the mold wall. And we found that the largest families are actually positioned at the mold wall. And this is because all the dendrites slightly deviate in their growth direction. So there's the mold wall and there's a deviating angle. So there's space left over, and the space is filled by continuous branching events. And yeah, you can see some parameters of this thing here. And we can do other things. We can observe, again, we slide from bottom to top, and we can observe how this dendrite family actually grows from the mold wall into the sample surface. And yeah, there's other things to say, but I don't. So, and we can also search for other special dendrite constellations. Maybe we are not interested in the interaction with the mold wall, but we're interested in the intrinsic competitive growth of dendrites. So what we did here is we have searched for dendrites that are misoriented compared to its surroundings. So this red dendrite here is completely misoriented, what means completely, like 3-degree misoriented to its surroundings. And we were very surprised to see what happens, because usually people think if there's an individual dendrite misaligned, usually it gets extinct. It is like the fish throwing, swimming up the river, right? It doesn't stand a chance against the velocity of the river. But actually, it's not what's happening. So this one individual dendrite manages to branch off. It creates a dendrite family, and on its way through on its misaligned way through the dendrite field, it provokes multiple branching and multiple extinction events. And this type of information we can only access because we have followed all the dendrites and also captured all of the relations. We can not only extract specific constellations from this database. What we can also do is we can, of course, do overall statistics of the entire dendrite population. For example, we can investigate the evolution of dendrite spacings by using a Voronoi deceleration. So for each dendrite, we identify the neighbors, we are measuring them, we're calculating the average distances, the smallest spacing, the largest, whatever. We can get information about the evolution of family size, and what's also interesting about the evolution of branching and extinction events. And what you can see is that the branching as well as the extinctions become more and more over the course of crystal solidification. And this is because the crystal mosaicity gets worse. The orientation spread of the dendrites becomes larger, so there's more competitive growth, there's more branching and extinction events. And we can even go further. We can now separate the contributions of these branching and extinction processes in what's happening at the mold wall and what is intrinsic to crystal solidification. And the blue line on the top right symbolizes the branching, the extinctions, the branchings at the mold wall. It stays constant, right? It doesn't matter how long the crystal is. It is just the dependence of geometry of your sample, while the intrinsic branchings, they increase. And they increase again because the orientation spread gets larger. So we are currently trying to even go a step further. So I told you in the beginning that we have a full representation, a digital twin of all dendrites in the 6,000 cubic meters volume. But to be honest, this was actually a lie. We don't have full information. We have full information about growth paths and neighborhoods and branchings. But what is missing, there's much more information in the micrographs. What is missing is the dendrite morphology. And in the next step, we want to include the dendrite morphology. We have to use a little bit of a different network there. We use a semantic segmentation. I don't want to talk about this too much. And we have some first results. Okay. So now we are also able to implement the dendrite morphology into our database. And you might think, oh, now you have a completely different data. You must need a different software or whatever. No, this is exactly the same data as before. The only thing that has changed is the geometric representation geometric representation of the dendrites. These dendrite entities existed before as line segments, and now we just include, well, there is also a triangulated surface in 3D space capturing properties of the morphology. However, this is it is kind of tricky. You can see when we trace such a dendrite over the growth path, there are still many artifacts and so on. So we need to optimize our system. We just started off with this a few weeks ago, and we are having really much fun observing how these dendrites morph while they're solidified. So I have to switch gears now a little bit and come to a different topic, which is, well, I wouldn't say out of scope, but what we can also do in microstructure informatics is we can improve the capability of microscopes. And I did this as an example for EVSD measurements. So we stay in the same material class. Also here we can see the dendritic microstructure, and in the BSE image on the left there, you can already see there are different shades of gray in this dendrites, and this is because they are slightly misoriented. You know this. And then my colleagues wanted to characterize this with EVSD, and they came to me and said, well, Pascal, we only have a red image. If you look closely, there's some information contained, but not really good. So what I came up with is I developed an EVSD method that is specifically designed to characterize this crystal mosaicity, and the right image there was derived on exactly the same raw data, right? We didn't use a new microscope, a new detector whatsoever. It's just post-processing of the data, and we can, and also visualization. And now we can get much more information about this data. Well, how does it work? It is actually, but I have to say, I didn't invent these type of technologies. It's called a high resolution technology. There are professors like Angus Wilkinson and so on here. They work in this field for a long time. And I built up a method that is related to it. It follows a similar path, but it deviates in certain details because it's specifically designed for the dendritic characterization. And it works by using a cross correlation. So we basically take a reference Kikuchi pattern and then the measured patterns. We compare measured patterns with the reference, and there are tiny shifts around them, which we can capture with cross correlation procedure. Then there are geometric relations. So I can relate these shifts of Kikuchi pattern with misorientations. I don't want to talk about this too much. But what came out of this is, well, we are now able to characterize the nature of crystal mosaicity with EVSD with a very high precision. This has a precision of much less than 0.1 degree, or a few hundredths of a degree, and this wasn't possible before. We have developed some specific color codings that are more suitable for these type of materials, and we can calculate the G and D density, as you can see there in the bottom. Right now, we are investigating these small angle grain boundaries that form in between the dendrites with TM, and compare the dislocation analysis with what came out of the EVSD. And what was very, very nice, we were actually the first that used or that investigated 3D printed single crystals. So our colleagues in Erlangen, Professor Körner, she's able to build up single crystalline material by additive manufacturing with the SEBM procedure. And we were the first that observed, well, also these materials exhibit something that is similar to a crystal mosaicity. Probably the mechanisms why the cells are completely other ones. There are certain ideas. We are not 100% sure of how this is, but yeah, maybe we can talk about this later. So I already want to come to an end now, slowly, and want to summarize what I was talking about. So when I'm doing microstructure investigation, my goal is always the same. It doesn't matter what material, what imaging technique, so my goal is I want to create a digital twin of the microstructure based on relational geometric ontology. And this is, I believe, already a good hint for you what you should consider when you want to do something like this yourself, because many students are walking around in our institute and they have micrographs and they want to use some AI, but they don't know what to do. I always say, well, what are the entities you are interested in and what are the attributes? And if you have realized what this is, oftentimes it becomes more clear what kind of computer vision technology you should use. So this is the architecture about this of my approach here. Right, there might be different types of image databases. We can use computer vision to extract the entities and put them into a microstructure database. The relations point to different object entities, but I do not want to repeat all of this now. And what we can do is we can extract geometry of certain subsets of entities or statistics about their attributes. And actually, these statistics about the attributes can then be used as descriptors for generative models. So basically what I do is a step in between. I don't try to transform the images directly into some descriptor. I first want to build up 100% digital twin, lossless, all the entities, and then I still can derive a descriptor and put it in the model for some simulation people. Yeah, and actually everything I do is always just a tool to get to this microstructure database. Yeah, these computer vision things, I'm not interested in this, to be honest, right? They change every 6 months. I will just take whatever there is, and I just need to extract the information about the entities. Same is true for the improvement of the microscope performance, right? By myself, I'm not interested in how good the microscope is. I want to resolve my entities, and sometimes it is necessary to increase the performance of the microscope to do so. So let me come to some final thoughts now. So I hope that I could convince you that such an approach can be very beneficial. For example, in a specific research project, as I've shown you for the dendrites. So if we do this for dendrites, we can extract much more information we can try to interpret. But this is, in my opinion, not the most profound implication of this. But think about, we are not doing this only in one research project, but this is being done in all research projects, and we will extract the entities and put them all in a centralized database. Suddenly what I can do is I can filter out, or I can extract different subsets of entities, and this could be, I don't know, give me all grains that have ever been observed in steel, right? And you get a huge set of entities, and you can quantify them. Or you are not interested in a specific alloy system, you are interested in abnormal grain growth. You can extract, so you can pull out all grains that are much larger than its surroundings, no matter what alloy system, right? And then you can investigate these subsets of the database in more detail. So, and if you followed me up to this point, the only question left is, well, how do we organize this kind of transformation, right? So who should do it, and how is it being done? And this is kind of a problem, because most of the research is being carried out by PhD students, postdocs, or even master students and so on. But I don't believe that they have enough time to develop all of these things for their own, because it's complicated, right? Oftentimes they lack the education. We material scientists do not have enough knowledge about computer vision and these database structures. And this is why in Bochum we founded this focus research group, where I try to bring people together that have a combination of certain skills, right? And it is very important to have this combination. So you need to be very experienced in microscopy, because microscopy, it is an art for itself, right? You need to have a good understanding about microstructure. I believe everybody here has a good understanding of microstructure. This is not a problem. And you need to have good understanding of informatics. And oftentimes these two things are the problem, right? There are people, experimentalists, they know exactly how to operate the microscope, how to prepare the samples, and how to interpret different contrasts of the microscope. But oftentimes they are not so much into informatics. Then we have many people in simulation and computational material science. They are experts in informatics, but oftentimes they probably don't have the best understanding of microscope and sample preparation and how this affects, the appearance of all these entities. And yeah, and I'm very curious to hear what your thoughts about this are. How do you want to organize it in your department? How should it be done? I believe education is an important factor, right? The students have to learn all this kind of techniques to be able to implement them in their projects. And yeah, I have to say, most of this research is actually not published. And the reason for this is this ancient habilitation thing in Germany. So, I mean, there are different ways of doing this, but I'm doing it probably the wrong way, the hard way. I have to write a manuscript, right? And in the law, it says the manuscript must contain original research, what they call, so it has to be unpublished research. So I'm kind of holding this back, and I'm right now writing it down. And you are actually one of the first people who are presenting this in such a detail, at least international, right? People at home know this. Yeah, and this is why I'm especially interested in what you think about my approaches, especially if you see flaws in it, right? If you can think about something that it cannot capture, please tell me, because now I still have a little bit of time to think about this. And with this, I am at the end. Thank you very much for your attention.
Thanks, Pascal. Floor is open for questions. I should add that I was disappointed not to see computation on the video side.
Yeah, maybe next time.
Yeah, I just want to thank you. This was a really fascinating presentation. And I think that definitely has a lot of use cases. I did have a question about the slide that showed the grain growth of the dendrite. If once the message is sent, we can go back to that slide.
If I can.
Oh, I'm sorry.
Let me finish.
Yeah.
Yeah.
Well, it just
not-
basically the
yeah.
dendrite that was growing, you could see that it changed shape every so often.
Yes.
Which likely was because of neighboring dendrites that were appearing or disappearing based on a layer.
Yes.
What I was curious about though is it seemed like very regular intervals that it would change shape.
Yes,
And I
yes.
was wondering if you had any insight on that.
Yes, you are actually right. And this is just the reason for this is that all this zero sectioning is done manually. So we have students, they probably don't have the best light right now, but they have to prepare all the samples slide by slide. So this is why our zero sections have a thickness of 1 millimeter. Of course, in an ideal world, we would not have sections of 1 millimeter, but for 10 microns or whatever, and then we would have a much better business. But actually, this is a good example because all things I've shown you, right? There are always many steps in between that provide these results, and it's funny that you've mentioned this. So maybe I can. So what we actually do is we only have the morphology here and over there, and we use a morphing algorithm to interpolate the shape changes in these intervals where we have no information. There's probably a certain room for optimization here, but as I said, we are just starting. But in an ideal world, we wouldn't have to do this, right? If the slices were finer, yeah. I mean, this is the problem. I mean, I think theoretically, this infrastructure can be a real completely lossless twin of a microstructure. However, in most cases, we don't have enough data to make it. For lossless twin, what we would have to use is basically the position of each atom and the element of each atom. If I had this would be the perfect twin, but we don't have this. So we have to use entities on a larger scale. This is the story behind this strange intervals there.
Yeah. Okay, that's very interesting.
I mean, how much is scale of different features in the microstructure able to be captured in this sort of a thing? For example, in this, I've got sort of a grain scale orientation, and I've got the dendrite orientation.
Yeah.
But to your point, if I knew the position of every atom, say using APT, I'm operating a much smaller scale, but I could then use that to inform these different levels, or I could use physics-based models to supplement what I'm doing here. How easy is it to accommodate those sorts of other information sources?
Well, this is a very interesting question, and you are asking some things that I intentionally hold back in this. But there's other concepts that I can briefly mention here. So there's this concept of ensembles, right? Multiple entities make up an ensemble. So if you start off with individual atoms, they create an ensemble, and the ensemble would be a crystal, right? And the crystal could have, for example, I don't know, would make up a crystallite, right? The boundaries of this ensemble is the grain boundaries, and multiple grains can make up, I don't know, a larger scale, right? So there's this ensemble kind of, so there's a hierarchical order in this too. Actually, I know this because the topic of our research project is called From Atoms to Turbine Blades. So we are all the time doing a multi-scale investigation, and but I have to say I've not completely figured out how to do this, but this would be my approach, working with ensembles.
So people in this room, let's get a couple of questions from the audience that is you online folks. I think there are a couple of questions. One, Nazmul Hassan.
Yes.
Hassan, Nazmul, if you want to unmute yourself and ask a question, that's good. Or okay,
well, I can read.
Yeah.
Yes, I'm able to do that. So what software or application was used? So all that you've seen is self-developed code, right? And it's mostly done in MATLAB. We have some certain things that we do in Python, but only small. Most of it exists in MATLAB. But actually, I don't think that it really matters what coding language you use, right? Because the database itself, we export them as JSON files. So in whatever programming language you use, you can import the microstructure data file. Of course, then you would have to develop the methods to access the data from the database according to the coding language you use, right? But yeah, it's all self-developed code.
Ankit?
Yeah, I have a question. So yeah, thanks for the great talk, Pascal. So I have a question regarding if you have thought about if you could use a similar technique to map something like a dendritic to a seaweed transition. So a seaweed transition, dendritic to seaweed is something which is observed in alloys like aluminum, zinc, copper, zinc, and so on. And then in some other cases, we may also have something like a eutectic transition, which is a lamellar growth of microstructure to a dendritic or vice versa, say nickel zirconium kind of alloy. So have you thought about if your characterization technique could actually capture these kind of transitions?
Well, I would have to see the exact micrographs to definitely give you an answer, but I assume that is possible. Like you can, of course, you would need then different types of entities to represent, for example, the eutectics that you mentioned compared to dendrite, right? But yes, you've mentioned a critical point, and I'm aware of that. There are certain limitations to this approach, and the limitations is, I mean, this works very well for very defined, distinct objects. But for example, if I make an image of a cloudy sky, right, there are no distinct objects. And with this approach, then it becomes very, very difficult. But it doesn't mean that it's impossible. I have certain ideas how to deal with this. And if you have very smooth gradients, you know, like, I don't know, like a very faint kind of compositional change and so on, this is kind of tricky to capture with this method. But this is more based on the, you know, atoms and crystal and phase boundary, grain boundary, like the more. And I believe with this you can capture most of the microstructures. Of course, the smooth transitions might be a problem, but I would have to deal with it once I have to deal with them.
Okay, another question I had is, can you also determine if dendrites tend to sometimes coarsen and fragment? So dendrites, not while growth maybe, but if they are sort of just annealed for a longer time, they tend to fragment and they also tend to coarsen. So have you thought of applying your technique to characterize those kind of microstructures than just the directional case that you talked about?
Yes, sure. However, of course, in our research project, we try to manufacture the best possible single crystals, right? So we only have very few examples where we have these slivers or this, you know, this breakdown of the dendrites. Of course, this would be an interesting research topic, but for the development of such a method, it's oftentimes better to use, you know, an easy case, right? And you can capture all the reactions there. Then you can go to, you know, these more extreme cases when something in the dendritic microstructure breaks up, you know, or when yeah. But yeah, we are thinking about this. Yes. Sure.
All right, thank you.
Yes.
Anyone else online? Let us know. Otherwise, we'll switch to Waterloo, who's here.
Yes. So this method is, so it depends on how you come up with entities and attributes, right?
Yes.
Like you have to have like a valid entities for specific program. So like I wonder if like maybe you may find like unexpected entities or attributes that you will never come up with. Like how can you have those kind of findings if you are restricted to that?
Yeah, you're exactly right. So this ontology is based on, there's a huge human bias to it because it is based on what we're doing in material science for 100 years, right? I would, in the first step, define the entities with what we know in the literature. This is what I told you, right? There are 1,000 papers of grains, thousands of grain boundaries, of precipitates, of carbides, whatever. And I would start to just use these entities. Of course, you're right. We might get into trouble if there's something completely unexpected, right? Then, yeah, we might have a problem. But what we can do for now is if we find, you know, a region in the microstructure that we cannot assign to a specific class, we will just say, well, this is ambiguous. Right, and then we end up with the leftover pieces which are ambiguous, and maybe later on we can characterize the ambiguous parts. Right? Who knows? This is how I would approach this.
Alright.
Yeah, good question. So if we build a database around entities, and then as you mentioned, let's say we acquire grain, let's say 42 micron
Mm.
fluid diameter from all alloys. My question is that out of the context of individual microstructures, the absolute acquiring based on a certain value may not need much, right? Because let's say in a certain microstructure, there can be one abnormally grown grain, which is very different from everything else, or a particular slice only touched like the very top corner of a grain and it looks small, but it's much smaller than everything else in the microstructure.
Of course, you are exactly right. But and this is, of course, if I have this database, it doesn't mean that I can extract random data and expect this to be meaningful, right? I need to interpret the data in the context of its surroundings, right? So that I don't get, the one individual large grain from this sample and the ordinary large grain of another sample. And this is exactly why we have these relation entities. So if you want to extract certain information, you should always consider what are the relations that are also of matter.
I think there's an online question from SK. SK, if you want to ask the question.
Yes, can you hear me?
Yes.
I have a question. So thank you for the presentation. So what you have is one microstructure, and then you have a digital twin of that microstructure. So my question is whether it's a equilibrium processing or non-equilibrium processing, you can get many different kinds of microstructures. So how do you capture the different variables in processing, which can reflect, what you are doing?
Well, this is a good question. All the questions are pretty good, and well, this is a philosophical debate now. But how can I? So, in my opinion, the information about the manufacturing parameters should be should be stored right here with the raw data, right? So the raw data should be connected with how it was manufactured. Because I don't want to blow up my database. Well, I am dedicated for microstructures. Later on, and of course, this would be the next step then to think about what kind of interfaces can we do to connect it to the manufacturing database or to the property database. But in my opinion, this information should be stored somewhere else, and it should only point to the raw data. So I mean, this is up for debate, right? I could of course also include all the parameters of manufacturing into each object entity. Right, so that this grain has a huge list, of attributes. What was the powder? What was the scanning? I could do this, but this would also blow up the database. I'm not sure if this is the right way to do it. But as I say, I'm not sure. I mean, I'm open for discussion about this and how to implement these other parameters from manufacturing end.
So for a given material, you could have 10 or 20 or 100 digital twins. Right? For a given material, you're making a material and you'd have 100 digital twins. So all you're doing is you have a microstructure and you have a corresponding digital twins without any relation to how that material was made. So like I do chemical vapor deposition, I have 7 variables or 8 variables, and I need to do design of experiments. So you could have so many digital twins for a given material. So I just have a difficulty really relating to what the kind of stuff you're doing.
Well, you are using the term material completely different than mine. I would say you have 7 different materials, right?
Yeah, exactly. I have 7 different materials, but the composition might be the same.
Yeah, but the parameters in manufacturing are different. Right?
Yeah, exactly. Yeah. So how do you capture that? That's my question.
In my opinion, it shouldn't. I mean, I could capture this on the object entities, but I think it is more elegant to connect the raw data, the images, with the manufacturing parameters, because they have to be stored somewhere too, right? There have to be raw data deposit databases, and in this raw data, there should be defined, well, how did this raw data how was it produced? It was produced by cutting a sample out of material that had a history of manufacturing, and what came out was an image. Right, and I'm just pointing to this image, and of course, this pointer also then includes all information that is all the meta information that is stored for this image. But you are right; it could be done differently. I could also pull out all this information and write it as attribute in my entity. This is, but then the nice thing here, this is a very sparse representation of microstructures. It's very efficient in terms of size. If I pull in all the data, suddenly I have a huge database, which is terabytes of data. But you're right, there are different ways of doing this. I'm not sure what is the right way to do.
Here,
Thank you.
We know how prankster can fairly easily make a chatbot racist, for example,
Yes.
meaning the result is only as good as a database.
Yes.
And my question is, how robust do you think it would be? Because we all know that sometimes there is bad data in
Yeah.
publish.
This is actually a big problem, but I got some I got inspired about for your cyber worlds that you are building up here at the university. And actually there is a project which could be applied for this too, which is almost like a democratic voting process. So you can have the raw I don't do this right now. So I have students who control the data. But what should I do? So I have a suggestion from the AI, and then there are students sitting and checking, well, okay, this is right, this is not right. Of course, if we would scale up this approach, then you can have a voting system, right? And all the scientists, if they have 3 minutes, they can click through and say, oh, no, this is not a grain, this is a dendrite or whatever, right? But of course, all this infrastructure simply doesn't exist, right? And I don't know of a better way than voting. I mean, what is a philosophical debate, right? What is the, I mean, if you're familiar with micrographs, there are oftentimes constellations where you say, I don't know what's going on here.
But I mean, to Pierre's point, you can actually train based on, you can create your own artificial but wrong microstructures and train the learning to distinguish. In principle.
Yeah, but then you need to make sure that the artificial microstructure has exactly the same flaws than what we get from the microscope, right?
Yeah, no.
Yeah.
Cool. Any other questions?
Just be completely practical. How do you do the sequencing of each layer practically, experimentally? Is it done in situ with like ion milling, or is it done?
That would be nice. No, ion milling. So we have the diameter of our sample is 12 millimeters, right? With the ion milling, we would spend a lot of time. So what it's actually done all manually, right? So our students are rotating around and doing this, and we have a spark erosion machine, and the spark erosion machine slices the sample. Then multiple of the sample needs to be embedded. They need to be polished, and then to be etched, and people are doing the optical microscopy. But of course, this is a good point as well, because the whole tendency in material science is to go towards this high throughput characterization. And for high throughput characterization, we would have to automate all this process of collecting hundreds or thousands of samples. But unfortunately we don't have this at home, and I have no experience with this. So, but it's probably important.
That's why we have that. Anyone else?
I'm a green people, so here, my name is Marcus. I just want to, I noticed, I just tried this database on some previous data that not designed for that. For example, in a lot of large company, I know that they have a database of microstructures and a system. For example, the ANSYS, they have something like that. If you have it try to use it to try to extract some information from the system for the database that not originally built for this.
I mean, what do you mean by not built? I mean, the thing is, this has to be built for each specific project again. But I have not built the full infrastructure. I've developed the general concept, and now for each specific type of microstructure, you need to fill it in with life, basically. So you need to determine, well, what in my microstructure, what are the relative entities, what are the relative relations, and how do I represent them? And then you just add this to the microstructure. This is not a full representation. I have no idea. There are so many different materials. I would not I would not be so egocentric to say I know for all the other microstructures what entities they have to be. And I believe this has to be a bottom-up process, right? The people who are very specialized in certain types of microstructure, they need to come up with what entities they need and what attributes they want to assign and measure. That's what I believe.
Okay, thanks for Pascal. This went way past our cutoff, but I guess that's okay. Thanks all for for engaging and very useful discussion. Okay, thanks, SK. I will let Pascal know about this.